Hey everybody, Morgan here. So we are in the AP Chem lectures about thermochemistry. We are on page 4 and we're going to be talking about the first law of thermodynamics today. Now, typically in physical chemistry classes, we say that the first law states the energy of the universe is constant. Now that is stated many different ways depending upon what class you're taking. Some say energy is conserved. Some people say you can't create energy, you can't destroy energy, you can only move it around, okay? Any of those are fine. But typically in chemistry classes, specifically physical chemistry classes, we say the energy of the universe is constant, okay? Now, that can be expressed as an equation. Delta E equals Q plus W. All right? The change in energy is equivalent to the heat and work. So, E being a capital letter, energy is going to be a state function, and we talked about state functions in our last set of lectures. All right. So, this concept allows us to introduce the idea of enthalpy, the heat released in a chemical reaction at constant pressure. Most of what we do happens at constant pressure anyways, so we can basically say that enthalpy and heat are the equivalent in our classroom situation. So, mathematically, H is defined as E plus PV. Now, since these are enthalpy and energy state functions, pressure is not, lowercase volume is, we need to talk about delta H. Delta H would be equal to delta E plus P delta V. And we know from the first law that delta H equals Q plus W plus P delta V. In our last set of lectures, we established that work is equal to negative P delta V. Therefore, delta H equals Q plus negative P delta V plus P delta V. Those two cancel out, and delta H naught equals Q. Enthalpy is heat. Now, very typically, what we will do is we will put a subscript P next to the Q just to indicate that pressure is being held constant. That's actually a notation that we're borrowing from calculus and doing something called a partial derivative. Okay, now, delta H naught, the way I wrote it right here, is to oppose all those other places. That little degree sign looking thing, okay? That means standard conditions. So what we're talking about would be 25 degrees Celsius. If we have gases, their pressure would be 1.00 atmosphere. And if we have solutions, their concentration would be 1.00 molar. Okay? Now, naught is a word we borrow from the British, meaning nothing. Okay? So delta H naught is nothing out of the ordinary. Okay. Cool. Little background for you there. And now into Hess's law, which states that heats of reaction are additive. Go to your math books and remind yourself about the additive property. So I'm thinking of the reaction 2NO gas plus O2 gas to give N2O4 gas. And I want to know delta H naught for this reaction, except I don't know it. But what I do know is delta H naught for the reaction of 2NO and O2 to 2NO2, which is negative 114.14 kilojoules. And I know for 2NO2 to N2O4, which is negative 57.20 kilojoules. So I can add those together. I can realize that a state function is independent of path. So it doesn't matter whether I go from here to here. I can go here to here, here to here, and I'm going to end up with the same value, which is negative 171.34 kilojoules, if I did that right in my head. Yeah, I'm pretty sure I did. Okay. So with state functions like delta E or delta H, we just care about the final minus the initial values. And we will always be happy with those. Okay? All right, so that is page 4, and we'll come back with page 5 in the next video.